Good morning. This is our second lecture for the module. As I indicated to you last week, my plan is to start recording them. Unfortunately, I've hit a snag with the software that I'm using to record the lectures, and so for this week we'll still have the lectures, this one for today and the one on Thursday evening in its time slot. If someone can just confirm that you can hear me, just by typing. Okay, perfect, you can hear me. So that's good, so we'll continue. I've got another module that starts, it's a first year module that starts in the first week of March. And unfortunately, we have a clash for the Tuesday, for this Tuesday period with that module. It's not a clash that you have, it's a clash that I have. So, in fact, I will have to start recording the lectures for you because I won't be able to go to both the first year lecture and this one. So for this week, we'll do the lectures in the lecture periods, which are this period and the Thursday at 6. If you can't attend, that's fine. The Collaborate sessions are being recorded. I'm recording this one, so if you can't come to Thursday evening's lecture, that's fine. You can download it and watch it afterwards. Okay, so let's get started. I still owe you example 14 from lecture 1, which is something I will record and post the video of instead of doing it in a lecture. For today, we'll move on to the next topic. And for tomorrow, we will definitely do an interactive tutorial session for the double period starting the same time at 9:40 tomorrow morning. Okay. Web work. I'm in the process of building your first exercise set. I will make it live a little bit later today or tomorrow morning at the latest, and then you will have 4 to 5 days to complete that first one. The next one we do will either be next week or the week thereafter. So please watch the announcements around web work exercise sets. Okay, I'm going to share my screen now and we'll get started with the lecture. Okay, here we go. Okay, so in the first lecture, we spoke about this concept of a sequence. And a sequence was a particular kind of function. In this lecture, we continue with the topic and we talk about a particular kind of sum. And in dealing with that sum, we will go back and use the concepts that we introduced in the previous lecture. This will always be the case. So next week, you will need to have a basic understanding of what we did this week for you to be able to follow along in the lecture. Just one more thing I need to say before we get into the content. This material is quite dense. So you are, and this is the case for all mathematics and probably for your other modules as well. I don't think mathematics is particular in that sense. And what I'm trying to say is you are never going to understand every single step of the calculation during the lecture. There's just too much detail there. So the lecture is really to show you what it is that you have to go and study yourself afterwards, right? For today, we should get halfway through the examples. In other words, we should get up to about example 6. There are 11 examples in this section. And the remainder of those we will cover in Thursday's lecture. Okay, so let's get started. Now, I'm going to remind you what we mean by the set R. The set of real numbers consists of 2 subsets. The first of these subsets is the set of rational numbers, and the second is the set of irrational numbers, right? There isn't a standard symbol for the set of irrational numbers, and we don't need them. We don't need such a symbol. So we will talk about this without a symbol for the irrationals. Let's get back and ask what we mean by a rational number. Well, a rational number is a number that can be written as the ratio of 2 whole numbers. That's where the word rational comes from. So if you look at a half, its decimal expansion is 0.5, which is also 0.5 with an infinitely long string of zeros after it. And that infinitely long string of repeating zeros is written as 0.5 0 bar. 6 divided by 5 is 1.20 bar because it's got an infinitely long string of zeros. 157 divided by 495 looks like this: 0.3171717, and the 17 repeats infinitely far, and that's how we write it. Now, this is what a rational number looks like when we look at its decimal expansion. There will always be some kind of repeating pattern. What about irrational numbers? Okay, how do we characterize them? Well, they will also have an infinite decimal expansion, but now the pattern will not repeat. So if we look at a number like pi, for example, pi can and has been calculated to many, many millions of decimal places. For the first, however, 15 or so, we can write pi as what you can see on the screen. So what do we mean by this? Here's what we mean. We mean that pi is equal to the number 3, the whole number 3, plus 1 divided by 10, plus 4 divided by 100, plus 1 divided by 1,000, plus 5 divided by 10,000, plus 9 divided by 100,000, and so on. 2 divided by 1,000,000, 7 divided by 10 million, not 7, 6 divided by 10 million, 5 divided by 100 million, and so on. And so the more of these decimal points we include, the closer we get to the actual value of pi. But this raises a new question now. What does it mean to have an infinite, because now we've got an infinite sum of terms, right? So what does it mean when we have an infinite number of terms? And something that should immediately be clear to you is that when we have an addition like 3 plus 5, or even if I add 100 numbers or 1,000,000 numbers, that's still a finite list of numbers that I'm adding. If I'm going to add an infinite number of numbers, then I'm doing something that's fundamentally different from what you've been doing in school when you add numbers up to today, right? And so this is what the topic for this lecture is. What does it mean when we have an infinite number of numbers that we add, and does it in fact make sense to talk about such a thing? Okay, so now suppose we've got this infinite sequence an starting from 1 to infinity, and we add all of them, then we get an expression that looks like this: a 1 plus a 2 plus a 3 plus a4, and so on. There's the general term an, and we know after an, we'll still have an infinitely long list of terms that we add. Okay. Now the first thing is to introduce a name for it. So the name for a sum like that, an infinite sum, will be called an infinite series or simply a series. And we will denote it just like we had a symbol to denote a sequence, the curly braces and the an inside. We have this sigma symbol. So we can have the sum symbol from 1, where the upper and lower bounds of the sum are indicated, n equals 1 to infinity of an, or in many cases we will ignore that, right? We won't explicitly say that it's an infinite sum. You will understand that it's an infinite sum of numbers. So there's the new topic for today, or for this week, an infinite series. And in reality, we only need sequences because we want to get to series. So really, this is actually the real content of the module, right? Because towards the end, in section 10, 11.9, 10, 11.8, 9, and 10, we'll start seeing what we can do with these things called infinite series. But they're built on top of the concepts of sequences. Okay, so now this raises the question, how do we make sense of such an infinite sum of numbers? So when you first think about it, the immediate examples that come to mind are examples where it seems not to make sense of such an infinite sum. And the reason it seems to not make sense is the immediate examples are examples where if I'm going to add an infinite number of these terms, they won't converge to a number. They'll just get larger and larger and larger, right? Which means we always get infinity. So for example, if you look at the sequence an, where an is equal to n. So a1 is 1, a2 is 2, a3 is 3, and so on. If we had to calculate that sum, what would we get? Well, you can see that this sum is something that gets larger and larger, right? So this doesn't go anywhere. It balloons up to plus infinity. And so this is an example where we don't get anything interesting coming back. It's kind of what we expect to happen. Let's look at another one. Let's look at a sequence where the nth term is given by 1 over 2 to the n. And we're going to make an infinite series of this sequence an. So the sequence we generate looks like this. The sum from 1 to infinity of 1 over 2 to the n is going to, when n is 1, it's a half. When n is 2, it gives us a quarter. Remember, this is not a sequence now, this is a series. So we need to add the terms. So it's a half plus a quarter plus an eighth. The next one's going to be 1 over 16. And we add it. And in general, we will add 1 over 2 to the n. And we'll continue infinitely far. And so I'm going to show you, not 100% logically yet, it comes later in the lecture, that this actually does not become infinite. In fact, the sum never even reaches the number 1. Okay? A little bit later in the lecture, you'll see that this particular series is called the geometric series. And its sum up to n terms is given by the expression 1 minus 1 over 2 to the n. And so you can see from that expression that the part that is 1 over 2 to the n is always positive, and I'm subtracting it from 1. And so you can see that infinite sum never even becomes 1. But it does get closer and closer to 1, right? And so let's have a look at the patterns first, right? For one term, the sum is a half. For two terms, the sum is a half plus a quarter, which is 3/4. For three terms, the sum becomes 7/8. For four terms, the sum becomes 15/16. You can go and double check the details of the calculation. When we get to n terms, we'll get to 2 to the n minus 1 divided by 2 to the n. And you can see that the larger I make n, the closer the sum gets to 1. And so in this particular, for this particular series, however we define, remember, I haven't defined yet what we mean by this infinite sum yet. But whatever that definition is, it would be great if the definition applied to this particular series means that that sum is 1. Because the closer we get, the larger we make n, the closer this sum gets to 1. And for this one, we will write that infinite sum is 1. Okay. So how do we do this? Okay, so here's what we're going to do. We are going to take an infinite sum and we will define a new sequence. So we will take a series and we'll create a new sequence called the sequence of partial sums as follows. So there we've got an infinite series, the sum from 1 to infinity of ai, right? Now remember, now I is the index. I'm just using a different letter because I need n for something else. And notice that from this, if we look at the individual terms that we add, we make out of that a sequence, right? And now we do the following. We define a new sequence represented by the letter S. And we say S, its first term is the same as A1, but its second term is A1 plus A2. Its third term is A1 plus A2 plus A3. Now you can guess what the fourth term is. It's going to be A1 plus A2 plus A3 plus A4. And now you can guess what the nth term for this sequence, this new sequence S is. It's going to be the sum up to the nth element of the original sequence AN. And now we are going to define what we mean by this infinite sum that we started with, this infinite series, the sum from 1 to infinity of ai. We're going to define it in terms of the convergence of this new sequence that we've created, the sequence of partial sums. And this is how we do it. All right? We say, given a series, the sum from 1 to infinity of an, right? Notice there's no limit. There's no end. We're taking all of the indices, right? We're summing up to infinity. Let Sn denote its nth partial sum. What do we mean by that? That's what we mean. We sum the individual components, the individual terms of the sequence An up to the nth element. And then we say, if this sequence, the sequence Sn, is convergent and its limit is equal to S, and it exists as a real number, then the series, the sum N, is called convergent, and we say that its value is equal to S. And the number S is called the sum of the series. If the sequence Sn is divergent, then the series is divergent. So the sum of an infinite series is the limit of the sequence of partial sums of the original series. Right. And so now you can see you're not going to understand series unless you've got a fair grasp of what happened in last week's lectures. Because in order to define what we mean by this infinite sum, we need to understand what we mean by the convergence and divergence of the concept of a sequence. Okay, let's look at an example. Suppose that we know that the sum of the first n terms of the series, the sum from 1 to infinity of an is Sn equals a1 plus a2 plus up to an is 2n divided by 3n plus 5. Then we know that the sum of the series is the limit of the sequence Sn. And so the sum from 1 to infinity of an must be the limit as n goes to infinity of Sn, which is the limit of the 2n divided by 3n plus 5. N goes to infinity of 2n divided by 3n plus 5, which is equal to, and now I use again the technique which I reminded you of in last week's lecture, which really comes from 1a, which is to say, I look at the highest power of the variable in the denominator, and to calculate that limit, I divide numerator and denominator by that highest power, and then I let n go to infinity, and I see that the limit is something, the detail I haven't written out is the detail around using the limit laws, right? Because what's there, before you get the final equal sign, you can say it's equal to the limit as n goes to infinity of 2 divided by the limit as n goes to infinity of the denominator, and so on. That final answer is 2 divided by 3. Let's look at another one. So here we'll talk about the geometric series now, right? And of course, the geometric series you've seen at school as well. It's not your first experience of it. So an important example of an infinite series is called the geometric series, and it looks like this. A times r plus a times r squared plus a whole lot of terms. The general term looks like this, plus ar to the n minus 1 plus, and then a whole bunch of terms coming, infinitely many of them, and that's equal to the sum from 1 to infinity of ar to the n minus 1. And we usually expect that a is not equal to 0, simply because if a is 0, then we just get 0, right? If a is 0, then 0 occurs in all of the terms, and then the whole thing is 0. Notice also that to go from one term to the next term, we multiply by what we call the common ratio, and the letter we use for that is r. So we want to see whether this series converges or diverges for particular values of r. Okay? And so we will look at various values of r. The first one we look at is what happens when r is equal to 1. So when r is equal to 1, let's consider what our nth partial sum will look like. So Sn will be a1 plus a2 plus a3 all the way up to an, right? So the first term there is going to be a. Then the second term is going to be a times r, but r is 1. So it's going to be a plus a. And in fact, r is 1, so all of the terms on the left will be a. And so I've got n terms up to for the partial sum Sn. And so Sn must be n times a. And now remember, we're interested in the limit. And so when we take the limit of Sn, it either goes to plus infinity or minus infinity. When will it go to plus infinity? Well, if you think about it, if a is a positive number, then Sn will go to plus infinity. If a is a negative number, it will go to negative infinity. And we've sorted out the case r is equal to 1. The series does not converge for r is equal to 1. It diverges either to plus infinity or negative infinity. Okay, what about other values, right? So now we're going to use a trick to an algebraic technique. Let's not call it a trick, an algebraic technique to simplify the limit calculation. So when r is not equal to 1, we've got Sn written like that. Now we're going to take the same expression and multiply it by r and write it again. So we've got r times Sn is a times r plus a times r squared all the way up to a times r to the n minus 1 and a times r to the n. All right. What we're going to do now is we're going to subtract the one from the other one, and we get Sn minus r times Sn is a minus a times r to the n. And now I can factorize the Sn on the one side and the a on the other side. And I get Sn times 1 minus r is a times 1 minus r to the n, which means Sn is a divided by 1 minus r to the n divided by 1 minus r. And now I can calculate the limit. Right? So now we know from our previous lecture that when r is a number in between -1 and +1, what happens to r to the n? That r to the n goes to 0. And so the limit as n goes to infinity of Sn is the limit as n goes to infinity of a times 1 minus r to the n divided by 1 minus r. Now I'm going to multiply the a in, right? And I get a divided by 1 minus r minus a divided by 1 minus r times the limit as n goes to infinity of a to the r of r to the n. Now look at the part of the calculation that says a divided by 1 minus r minus a divided by 1 minus r times that limit. The first term there is constant. In other words, it doesn't depend on n, which means, remember, the limit of a constant is the constant, and that's why we don't need the limit on that first term in that part of the calculation. Since r to the n goes to 0 when r is in between -1 and +1, not including the endpoints, our final answer is a divided by 1 minus r. And so we can see that when the absolute value of r is less than 1, the geometric series is convergent and its sum is a divided by 1 minus r. Now, we've already handled the case r is equal to 1. We haven't looked at r is equal to -1. And we haven't looked at any value larger than +1 or less than. So let's look at those. Now, one of the theorems we did, one of the results we did in last week's lecture, so please go have a look at it, 11.1.9, the sequence r to the n is divergent for all those values of r. And so by equation 3, the limit as n goes to infinity of Sn does not exist when r has any of those values. Okay, so for these values of r, the geometric series diverges. We summarize the result as follows. The geometric series, the series from 1 to infinity of a r to the n minus 1, which is equal to a plus ar squared, and so on, is convergent if the absolute value of r is less than 1, and its sum is given by this expression a divided by 1 minus r. And that a, remember, is the first term in the series. Right? And remember that r is the common ratio. If the absolute value of r is greater than or equal to 1, then the geometric series is divergent. Look at another example. Example 3. Find the sum of the geometric series 5 minus 10 divided by 3 plus 20 divided by 9 minus 40 divided by 27, and so on. So the first term is 5. That's clear. Notice that the example says it tells us that it's a geometric series, right? And so we don't have to first convince ourselves that it is. The first term is a equals 5. The common ratio is minus 2 divided by 3. We see that because to go from the first term to the second term, we multiply the 5 by minus 2 over 3 and we get minus 10 over 3. And then to go from the second to the third, we multiply by the same number and so on. And so it's easy to calculate the limit of this, this infinite geometric series, this infinite sum of the geometric series, because we simply plug it into the formula. The absolute value of r is less than 1, and so the series converges by the previous result we had. And to calculate its sum, we simply plug it into that formula, a divided by 1 minus r, which is, gives us a final answer of 3. What about this series? Does it converge or diverge? Is the series the sum from 1 to infinity of 2 to the 2n, 3 to the 1 minus n convergent or divergent? So we recognize this as a geometric series, and we rewrite the nth term of the series in the form a r to the n minus 1 as follows. We say the sum from 1 to infinity of 2 to the 2n times 3 to the 1 minus n. I'm going to write the 2 to the 2n as 2 to the 2 raised to the power n. I'm going to change the sign of the n minus 1, the 1 minus n. Right? And now I can rewrite that as 4 to the power n divided by 3 to the n minus 1. I'm going to pull out one factor of 4, and I'm going to write this as 4 divided by 3 n minus 1. And we recognize the series is geometric with a equals 4 and r equals 4 divided by 3. Since since the absolute value of r is greater than 1, this series cannot converge, it must diverge. Here's a slightly longer but also more interesting example. Example 5. A drug is administered to a patient at the same time every day. Suppose the concentration measured in milligrams per milliliter is Cn after the injection on day n. Before the injection on the next day, only 30% of the drug remains in the bloodstream, and the daily dose increases the concentration by 0.2 milligrams per milliliter. We are asked to do the following. First one, find the concentration of the drug after the injection on the third day. What is the concentration after the nth dose? And what is the limiting concentration? Okay, so the first one. Now, just before the daily dose of medication is administered, the concentration drops to 30% of the previous day's concentration. In other words, 0.3 times Cn. And so Cn plus 1, the dose on the next day, must be 0.2 plus 0.3 times the dose from the previous, the concentration from the previous day, not the dose. Okay. And now that we've got this, what we call a recurrence relation, we can plug in the values of n, starting with n equal to 0, and get that C1 is equal to 0.2 plus 0.3 C0. Now C0 is 0, right? On day 0, nothing happens. And so C1 is 0.2. C2 is 0.2 plus 0.3 C1, which is 0.2 plus 0.2 times 0.3, which is 0.26. And we can calculate C3 in a similar way, and it gives us 0.278. And we've calculated the drug after the injection on the third day. What is the concentration after the nth dose? After the nth dose, the concentration looks like this. Cn is 0.2 plus 0.3 times 0.2 plus 0 times 0.3, and so on up to n minus 1. And this is a finite geometric series. And so we've got a formula to calculate that. That number comes to 2 divided by 7 times 1 minus 0.3 to the power n milligrams per milliliter. What about the limiting concentration? Because this value of 0.3 is less than 1. Remember, this 0.3 is now the constant R, constant ratio. We know that the limit as n goes to infinity of 0.3 to the n is 0. And so the limiting concentration is the limit as n goes to infinity of Cn is the limit as n goes to infinity of 2 divided by 7 times 1 minus 0.3 to the n, which is 2 divided by 7 milligrams per milliliter. We'll stop after this example, then I'll look at your questions. Write the number 2.3, 17, 17, 17, and so on as a ratio of integers. Okay, so we know that 2.3, 17, 17, 17 is 2.3 plus 17 divided by 10 to the 3. Right? Because the first 17 in the decimal expansion is 17 divided by 1,000 plus 17 divided by 10,000 plus 17 divided by 100,000. What's that? Not going to be 100,000. It's going to be 10 million plus 17 divided by 10 to the 9 and so on. So if we look at this, we've got a geometric, if we ignore the 2.3, what we have is a geometric series where the first term is 17 divided by 1,000, right? And the common ratio is 1 divided by 100, because you need 2 powers of 10 to go from 10 to the 3 in the denominator to go to 10 to the 5 in the denominator, to go to 10 to the 7 in the denominator, and so on. So our common ratio R must be 1 over 2, 10 to the 2. And therefore, 2.713 repeated is 2.317 repeated is 2.3 plus the limit of that geometric series that we've described. But that we can calculate using our formula. It's A divided by 1 minus R, which is 2.3 plus that 17 divided by 1,000 divided by 99 divided by 100, which is 23 over 10 plus 17 divided by 990, which gives us 11747 divided by 495. Right? And I think we'll stop there. I'm going to stop sharing. We've got a few minutes for questions. So let's see. I heard a few questions coming in. So let's see what you were asking about. R equals 1 converges to 1. DK, please explain the limit of R to the N. Go look at last week's lecture. Please explain how you pulled out 4 from the series. That's easy. 4 to the R is 4 times 4 to the R minus 1. Okay. How did you know? Okay, I see someone else answered that as well. When you multiple, you add the one. Okay. Okay, it looks like a lot of this is just you guys speaking to one another, so that's fine. Please explain example. How do you know that there will be a pattern of +2 in the denominator exponents? Because we go from 10 to the 3 to 10 to the 5 to 10 to the 7 to 10 to the 9. So to go from 1 over 10 to the 3 to 1 over 10 to the 5, I must multiply by 1 over 10 to the 2. Okay? And that answers mohuame as well. Okay? I think I've answered all the questions. Yo says R equals 1 converges to 1. R equals 1 converges to 1. I'm not quite sure, but I think you are talking about the geometric series, and in fact it diverges, right? Nondiza says so just above you. Okay. So the geometric series is always equal to 1. No. The geometric series that we looked at in the first example where I justify the concept, that one goes to 1. What the geometric series converges to depends on the starting, the first term, as well as the common difference. Look at example 2 or 3. There's one of them that's a geometric series that converges to the number 3, not to 1. Okay? I think that's it. We actually have 2 minutes left. So any other questions? No, it's just a minute left. Yes, I will post a link to the web work when it's up. I'm also going to post a PDF explaining how to enter answers into web work, right? Explaining how to enter answers into web work. I will post the link and I will post your details for logging in and so on. Ogare asks, so it's equal to the one that converges to. So it's equal to the number it converges to. Yes, Ogare. Baghdadi says, so in general, if R is less than 1, then it converges, and R is greater than 1, then it diverges. Yes, Baghdadi, it's better to say not in general, if the absolute value of R is less than 1. So I'm going to type here for Baghdadi, if the absolute value of R is less than 1, then it converges. Because the way you said it, R is less than 1 could include things like -10, right? But it doesn't converge for -10. It must be the absolute value of R. Please be careful, Mr. or Miss Baghdadi. Okay, cool. That's it. Our time's up. I shall see you tomorrow morning, same time, and then we'll have a double period during which we can talk a little bit more. And I want you to raise your issues. And then I think I'll make the web work assignment available to open immediately after that tutorial session. Okay, cheers guys, go do some maths. Bye-bye. That one solutions will come soon, Nondisa.